Substituting given values of 200 ohms and 47 microfarads, we obtain a time constant of 9.4 milliseconds for the discharge phase. So don't get confused, let's call the discharge phase's time constant tau2. We should therefore expect the capacitor to be fully discharged after 5 time constants, so 5 times 9.4 milliseconds would equal 47 milliseconds. You note a complete discharge phase of 47 milliseconds would be equal to the larger circuit's 150 plus 47, or 197 milliseconds. During the discharge phase, voltage across the capacitor would drop from 24 volts to 0 volts over a span of 47 milliseconds. During the discharge phase, current leaves the capacitor. By our earlier definition, this reversal of current flow must necessarily be negative. Discharge current out of the capacitor initially spikes and then degrades to 0 amps over a span of 47 milliseconds. With switch 1 open and switch 2 closed, the capacitor would discharge itself through R2 only. Thus, R1 experiences no current and no voltage drop during the discharge phase. Current leaving the discharging capacitor travels through R2 top to bottom. Since we're not beholden to any previous sign convention, let's assume this direction of travel is positive. Discharge current out of the capacitor and through R2 initially spikes and then degrades to 0 amps over a span of 47 milliseconds. Despite the coyness of the signs, it should be evident that the current out of the capacitor and into R2 are one and the same because they're in series with one another. Current through elements in series is the same. Now that we've got a general idea of what current and voltage looks like during the discharge process, see if you can derive the expressions for these functions during the discharge phase. Again, make your job easy and just assume that the discharge process begins at another t equals 0. This is not mathematically correct. However, it sure beats trying to include a 150 millisecond offset into your expressions. By all means, pause the lecture and try this on your own. If you're tracking, you should have come up with the following expressions. The discharge phase begins at the voltage across the capacitor from the value obtained during the previous charge and steady state period, in this case 24 volts, and then it drops to 0 volts over 5 time constants or 47 milliseconds. Vc of t during the discharge phase can be modeled as 24 volts times e to the negative t over 9.4 milliseconds. Or again, we are assuming a different t equals 0 for the discharge phase that is actually the larger circuit's 150 milliseconds. Given there are only 2 elements in this series discharge path, voltage across resistor 2, VR2, is effectively identical to Vc of t. VR2 can also be modeled as 24 volts times e to the negative t over 9.4 milliseconds. Any voltage rise induced by the discharging capacitor must be dropped across R2. The expressions for R1 during the discharge phase are super easy. Nothing happens. During the discharge phase, current leaves the capacitor. By our earlier definition, this reversal of current flow must necessarily be negative. Given 24 volts applied across a 200 ohm resistor, Ohm's law demonstrates this initial burst of outgoing current will be 24 volts divided by 200 ohms or 120 milliamperes. Current through the capacitor IC of t during the discharge phase can be modeled as negative 120 milliamperes times e to the negative t over 9.4 milliseconds. Since the discharging capacitor and resistor 2 are in series with one another, any current out of the capacitor must necessarily go into R2. This being said, we're not beholden to any previous definition of current flow, so we can say discharge current traveling top to bottom is positive for R2. Current through R2, IR2 of t, could therefore be modeled as 120 milliamperes times e to the negative t over 9.4 milliseconds during the discharge phase. Again, I need to remind you that these equations are valid for the discharge phase only, which begins at the larger circuit's t equals 150 milliseconds, which, to simplify our analysis, we're simply assuming is a separate t equals 0 superimposed upon the previous charge and steady state period. Long story short, use the charge equations from 0 to 117.5 milliseconds, use the steady state simplifications from 117 milliseconds to 150 milliseconds, and the discharge equations from 150 to 197 milliseconds. This is admittedly an organizational challenge, but should be well within your reach. As with our previous examples, several important takeaways should be immediately identifiable. During the charging process, current rushes through R2 and into the capacitor. While charging, voltage across the capacitor rises. During the discharge process, current rushes out of the capacitor and through R2. While discharging, voltage across the capacitor drops. Any voltage experienced by resistors R1 and R2 is simply the consequence of the incoming and outgoing current experienced by the capacitor during the charge or discharge process. Importantly, voltage across the capacitor, whether charging or discharging, never undergoes a disjointed instantaneous transition or sudden reversal. That's the point. Capacitors resist sudden changes in voltage and are often employed in circuits that necessitate relatively steady or slowly changing voltage conditions. Additionally, you will note the asymmetry of the charge and discharge process. This is a consequence of R1 being a 500 ohm resistor and R2 having a smaller resistance of 200 ohms. It makes sense that the quantity of energy stored in the capacitor during the relatively slow charge process is expended at a much faster rate because of the decreased opposition, thus a complete discharge occurs more rapidly. To further highlight this asymmetry, you will note that the current during the relatively rapid discharge process is much higher than that of the relatively slow charge process. Again, current is a measure of the time rate of charge transfer in units of coulombs per second. The complete charge process deposits a quantifiable amount of charges on the plate of this capacitor, where charge equals voltage times capacitance. In this case, 24 volts times 47 microfarads would yield roughly 1.1 millicoulombs of charge. During the discharging process, charge transfer rate, i.e. current, is much larger than that of the charge process, and it takes much less time to strip the same amount of 1.1 millicoulombs off the plates. It makes sense. Before we move on to the next example, let's perform some instantaneous analysis of the discharge process. Let's say we wish to know the instantaneous current out of the capacitor, voltage across the capacitor, current into resistor 2, and voltage across resistor 2 at 20 milliseconds into the discharge process, or 150 plus 20, or 170 milliseconds into the complete system's timeline. By all means, pause the lecture and try this on your own. If you're tracking, you should have arrived at the following values. If you're hard-headed, I suppose you could have substituted 20 milliseconds into each of the time-varying expressions to obtain the desired answers. However, here's a much easier method. Use one time-varying expression, and then just employ series circuit properties and Ohm's law from there. Substitute 20 milliseconds into the discharge phase's VC of t expression. This yields a value of roughly 2.9 volts. R2, being the only element in series with this discharging capacitor, must also have a voltage of roughly 2.9 volts. When roughly 2.9 volts is applied across a 200 ohm resistor, Ohm's law demonstrates that 2.9 volts over 200 ohms, or roughly 4.3 milliamperes of current, will be traveling through it. Given R2 and the discharging capacitor are in series with one another, this implies that 14.3 milliamperes is traveling out of the capacitor, where the negative sign implies a reversal of current flow during the discharge phase. Too easy. We can also go about instantaneous analysis in a different manner. Let's say we wish to know at what time voltage across the capacitor has dropped to 5 volts. What time value satisfies this condition? Here's a hint. Make the process easy and just use the discharge phases t equals 0 and then tack an extra 150 millisecond onto your answer. By all means, pause the lecture and try this on your own. If you're tracking, you should arrive at the following time. Ultimately, we're being asked to solve for the time value that satisfies the expression 5 volts equals 24 volts times e to the negative t over 9.4 milliseconds. What time value satisfies this condition? Divide both sides by 24 volts. Take the natural log of both sides. Remove the negative signs from both sides, and multiply both sides by the time constant. We obtain a value of t equals roughly 14.7 milliseconds. This is where we need to remind ourselves what this answer implies. Our answer of t equals 14.7 milliseconds means 14.7 milliseconds into the discharge process. From the larger system's perspective, this actually represents 150 plus 14.7, or 164.7 milliseconds. If you're ever asked to solve for the instantaneous values of current or voltage across R2 at this same time, I suppose you could substitute this same time into their time-varying expressions. However, there is a much, much easier way. If we know voltage across the capacitor to be 5 volts, this means voltage across R2 must also be 5 volts. After all, it's a series circuit with only two elements. When 5 volts is applied across a 200 ohm resistor, Ohm's law demonstrates 5 volts over 200 ohms, or 25 milliamperes of current, will be traveling through it. This implies that 25 milliamperes is traveling out of the discharging capacitor, where again a negative sign implies a reversal of current flow during the discharge process. Too easy. Let's examine the capacitor discharge process for one more system. Let's base this example off our previous example 3 from the capacitor charging lecture. You recall, example 3 was a series circuit consisting of an 8-volt source, a switch that closes at t equals 0, a 250 ohm resistor, and an initially uncharged 2 microfarad capacitor. During the charging process, we learned it had a relatively short time constant of 500 microseconds. IC of t during the charging process was 32 milliamperes times e to the negative t over 500 microseconds. Current through the capacitor experienced an initial surge of 32 milliamperes and decayed to 0 over 5 time constants, or 2.5 milliseconds. Vc of t during the charging process was 8 volts times 1 minus e to the negative t over 500 microseconds. Voltage across the capacitor started out at 0 volts and grew to 8 volts by 2.5 milliseconds. IR of t during the charging process also equaled 32 milliamperes times e to the negative t over 500 microseconds. Current through the resistor and all elements in series with it experiences an initial surge of 32 milliamperes and decays to 0 amps by 2.5 milliseconds. Finally, VR of t during the charging process was 8 volts times e to the negative t over 500 microsecond. Voltage across the resistor surged to 8 volts and decayed to 0 volts by 2.5 milliseconds. Note these functions are valid only for the charging process between t equals 0 and 2.5 milliseconds. Let's examine the discharge process for this system by including a very simple modification, that of switch 2 in the following location. Yes, this is different than our previous examples, but it's well within your capacity to understand how the system works with a little thought and investigation. First, for obvious reasons, one would never simultaneously close switch 1 and switch 2. The obvious reason being that the simultaneous closure of both switches results in a short circuit being applied across the 8-volt DC power source, through which theoretically infinite current will flow, since the source is being presented with 0 ohms of opposition. Switch 1 and switch 2 are at all times meant to be in opposing states. When switch 1 is closed, switch 2 is open, and when switch 1 is open, switch 2 is closed. Let's say they toggle states every 2.5 milliseconds. Consider a back-to-back charge and discharge process from 0 to 5 milliseconds. The first 2.5 milliseconds with switch 1 closed and switch 1 open is obviously characterized by the charge process that we previously examined. My question to you is this: what happens during the next 2.5 milliseconds when switch 1 is open and switch 2 is closed? Here's a hint. Consider voltmeters and ammeters placed in the following fashion. Voltmeter C reads the voltage across the capacitor plus to minus, top to bottom. Ammeter C reads the current through the capacitor in to out, top to bottom. Voltmeter R reads the voltage across the resistor, positive to negative, left to right. Finally, ammeter R reads the current through the resistor in to out, left to right. What happens during the discharge process? Importantly, which direction does current flow, and with what polarity does voltage appear? Also, consider the rapidity at which these electrical properties change. What's the time constant for the discharge circuit? By all means, pause the lecture and think about this. If you're tracking, you should have arrived at the following conclusion. During the discharge process, current flows out of the capacitor and through our only resistor right to left. Current flow in the whole system is reverse directions. The initial surge of outgoing discharge current must therefore be negative for both the resistor and the capacitor. As an additional consequence of this reversal of current, voltage across the resistor now appears positive to negative, right to left. We also might expect voltage to be negative for the resistor. Finally, note that the time constant for the discharge phase is identical to that of the previous charge phase, given we're employing the same resistor and the same capacitor value. The time constant for the discharge phase is also 500 microseconds, and we should expect the discharge to be complete after 5 times 500 microseconds, or 2.5 milliseconds, i.e. the larger circuit's 5 milliseconds. In summary, the discharge process is essentially identical to the charge process, only it's running backwards. Let's examine voltage across the capacitor Vc of t first. At the discharge phases t equals 0, i.e. the larger system's t equals 2.5 milliseconds, voltage across the capacitor will be the same voltage as that when the charge phase ends, in this case 8 volts. From here, the voltage across the discharging capacitor then decays to 0 volts over 5 time constants, or 2.5 milliseconds. Vc of t during the discharge phase can be modeled as 8 volts times e to the negative t over 500 microseconds, where again, we're assuming the discharge phase has a new t equals 0, which happens to be the larger circuit's t equals 2.5 milliseconds. During the discharge phase, current leaves the capacitor. By our earlier definition, this reversal of current flow must necessarily be negative. Given 8 volts applied across a 250 ohm resistor, Ohm's law demonstrates this initial burst of outgoing current will be 8 volts over 250 ohms, or negative 32 milliamperes. Current through the capacitor IC of t can be modeled as negative 32 milliamperes times e to the negative t over 500 milliseconds. Because there exists a single series path, any current out of the capacitor must necessarily go through the resistor. By our earlier definition, this reversal of current flow must also necessarily be considered negative. Current through the resistor IR of t can be modeled as negative 32 milliamperes times e to the negative t over 500 microseconds. Given this reversal of current travel, polarity of the voltage across the resistor must also be reversed. VR of t can be modeled as negative 8 volts times e to the negative t over 500 microseconds. As with our previous examples, a couple important takeaways should be immediately identifiable for the back-to-back charge and discharge process. During the charging process, current rushes through the resistor, left to right, and into the capacitor. While charging, voltage across the capacitor rises. During the discharge process, current rushes out of the capacitor and through the resistor, right to left. While discharging, voltage across the capacitor drops. Any voltage experienced by this resistor is simply a consequence of the incoming and outgoing current experienced by the capacitor during the charge or discharge process. Importantly, voltage across the capacitor, whether charging or discharging, never undergoes a disjointed instantaneous transition or a sudden reversal. That's the point. Capacitors resist sudden changes in voltage and are often employed in circuits that necessitate relatively steady or slowly changing voltage conditions. Additionally, you will in this occasion note the symmetry of the charge and discharge process. This is the consequence of the same magnitude resistor being employed for the charge and discharge path. It makes sense that the quantity of energy stored in the capacitor takes the same amount of time to accumulate and dissipate given equal transfer rates. Current during the charge and discharge phase are equal in magnitude, and a full charge takes just as long as a full discharge. Finally, you will note that the resistor in the symmetric charge-discharge circuit experiences an interesting phenomenon, that of alternating current and voltage. During the charge process, current and voltage appear left to right. During the discharge process, current and voltage appear right to left. If we consider only the mathematical average, one might be led to believe that on average, the resistor experiences 0 amps and 0 volts, thus 0 watts of power. After all, we're presented with equal and opposite magnitudes of voltage and current for identical durations. This is categorically untrue. Recall that power is the product of voltage and current. During the charge process, positive voltage times positive current yields positive power. During the discharge process, negative voltage times negative current yields positive power. Consider this plot of power dissipated by the resistor as a function of time. Both events, the charge and discharge, result in positive power being dissipated by the resistor. During the charge process, the resistor experiences a burst of positive power as the capacitor charges up. During the discharge process, any energy stored in the capacitor is dissipated by the resistor in another burst of positive power. Consider peak instantaneous power delivered to the resistor at the beginning of the charge phase at t equals 0 and the beginning of the discharge phase at t equals 2.5 milliseconds. These represent conditions of peak power delivery to the resistor. At t equals 0, the beginning of the charge phase, positive 32 milliamperes times positive 8 volts yields peak power delivery of positive 256 milliwatts, which drops to 0 watts by 2.5 milliseconds and the charge process ends. At t equals 2.5 milliseconds, the beginning of the discharge phase, negative 32 milliamperes times negative 8 volts yields a peak power delivery of positive 256 milliwatts, which drops to 0 watts by 5 milliseconds, i.e. 2.5 milliseconds into the discharge phase, and the discharge process ends. At all times, power dissipated by the resistor will be positive. Importantly, note that the resistor is not the only element in the system. Consider this plot of power dissipated by the capacitor as a function of time. Prepare yourself for something surprising, but if you've been paying attention, understandable. Let's examine power delivered to the capacitor during the charging phase first. At t equals 0, current flowing into the capacitor is respectively high at positive 32 milliamperes. However, voltage across the capacitor is 0 volts. Instantaneous power delivery at the beginning of the charge phase is 0 watts. That makes sense because at t equals 0, nothing has really happened yet, but the stage is being set. At t equals 2.5 milliseconds, voltage across the fully charged capacitor is 8 volts, but 0 amps of current is flowing into it. Instantaneous power delivery at the end of the charge phase is also 0 watts. Again, it makes sense because at 2.5 milliseconds, the capacitor is fully charged and the show is over. In between these times, something interesting happens. Power delivered to the capacitor rapidly increases, peaks, and then steadily decreases. I could mathematically describe this shape using an equation, but it's a bit of a goat show. The important take-home point is this. Power delivered to the capacitor during the charge phase is positive. This is understandable. The capacitor is sucking up power from the source, as is the resistor. Let's consider the source. From the source's perspective, it is supplying a total power equal to the sum of the power to the resistor plus the power to the capacitor. Plotted as a function of time, power supplied by the source in pink is also time variant. Note I'm using the term power supplied by the source rather than the term power dissipated. This is meant to imply that supplying power is different than the act of dissipating it. If I wanted to, I could just stick with the term dissipate and say the source is dissipating negative amounts of power, but that sounds kind of weird, especially for a source. Long story short, power in equals power out. Power to the source equals power to the resistor plus power to the capacitor. As long as you keep track of signs, it all works out. Now let's consider the discharge phase. This is where something weird but kind of understandable happens. Voltage across the capacitor is positive. However, current is leaving it and considered negative. Positive voltage times negative current yields negative power. Plotted as a function of time, power dissipated, note the term I'm using, dissipated is negative. What is negative power dissipated? Negative power dissipated is the same thing as supplying positive power. Note the equal and opposite symmetry of power for the two elements in the discharge circuit. Can you dig it? All of the power being dissipated by the resistor is not being supplied by the source, but rather the capacitor. The source has nothing to do with it. Plotted as a function of time, power supplied by the source during the discharge phase is 0 watts. In summary, during the charge process, the source deposits a packet of energy onto the capacitor. During the discharge process, that same packet of energy is released from the capacitor and the source stays out of it. Speaking of which, let's talk about energy again. If I didn't lose you earlier, hold on tight because I might lose you now. If energy is power times time, the energy delivered during each phase would be equal to the area under the power curve. For those with a calculus background, you'll know energy would be the integral of the power curve. The math is a little heavy, so here again is a convenient shortcut. The total energy inside a fully charged capacitor is equal to half the capacitance value times the final voltage squared. Because there is a relationship between charge, voltage, and capacitance, one can also solve for total energy stored in a capacitor as the charge squared divided by twice the capacitance. Substituting in our given values of 8 volts and 2 microfarads, we find this capacitor at the end of the charge process has stored a total amount of energy equal to 64 microjoules. Skipping the complicated math, assuming 100% efficiency, this is the same amount of energy delivered by the capacitor and dissipated by the resistor during the discharge process. The shapes do look different, but trust me, the area under each curve is also 64 microjoules. If you kind of squint your eyes just right, the excess area at the end of the charge phase kind of accounts for the lack of area at the beginning of the charge phase. In summary, during a complete charge phase, the resistor dissipates 64 microjoules. At the same time, the capacitor absorbs or stores 64 microjoules. The source must therefore have supplied a total of 128 microjoules during the charge process. Again, the area of the two power curves for the resistor and the capacitor equals the area of the power curve supplied by the source. Trust me, you cannot handle the math. If you want to get this lecture over in a reasonable amount of time, just go with it. While the quantity of energy dissipated by the resistor goes towards the production of heat, the quantity of energy consumed by the capacitor goes towards the establishment of an electrostatic field between the plates. Rather than using the term dissipated, it might be more appropriate to consider any energy consumed by the capacitor as absorbed or stored energy. It's essentially a spring coiled and ready to bounce. When the discharge process unfolds, the energy stored in the capacitor plates is released, returned, or better yet, supplied to the system. All 64 microjoules supplied by the discharging capacitor is dissipated by the resistor. If you want to think of it this way, during the charge phase, the source works real hard and supplies not only energy to the resistor, but also supplies a little extra to the capacitor. During the discharge phase, the source then gets to kick back and drink a mint julep out of a frosty copper mug on a shady porch while the capacitor does all the work. Regardless, the resistor experiences regular bursts of positive power, each burst delivering 64 microjoules of energy each cycle, regardless of which direction current is traveling. The math details are admittedly a little heavy, especially if you spent a couple years chained to a desk learning calculus. However, for our purposes, you only need to really concern yourself with the basics. During the charge phase, the resistor experiences time-variant positive voltage, positive current, and thus dissipates time-variant positive power. During the charge phase, the capacitor also experiences time-variant positive voltage, positive current, and thus dissipates time-variant positive power. Rather than going towards heat, this power, however, is directed towards the establishment of an electrostatic field. Thus, dissipate might not be the best choice of words. A better choice of terminology might be store or absorb. During the charge process, the source must necessarily supply both these expenditures of power. Power supplied by the source must equal the sum of power dissipated by both the resistor and the capacitor. During the discharge process, things flip-flop. During the discharge phase, the resistor experiences time-variant negative voltage, negative current, and thus still dissipates time-variant positive power. During the discharge phase, the capacitor also experiences time-variant positive voltage. However, current must necessarily be considered negative, and thus dissipates time-varying negative power. Thus, dissipate might not be the best choice of words. A better choice of terminology might be supply or return. During the discharge phase, the source kicks back on the porch with its feet up on a Yeti 110 full of silver bullets and watches all its hard work during the earlier charge phase pay off. In an ideal scenario, this process would be 100% efficient. However, in practice, we might observe some losses in the storage and subsequent retrieval of this energy. Alright, I do believe I've hammered you enough for today. We'll examine the capacitor charging process with initial conditions and partial charge and partial discharge scenarios in later lectures. In conclusion, we examine the capacitor discharge process. We learned a discharging capacitor can supply a burst of outgoing current, which then decays to 0 over 5 time constants. Voltage across a discharging capacitor drops from the previous charge value to 0 over 5 time constants. Current through the discharge path must equal the current out of the capacitor, and all voltage must be dropped across the discharge path. Finally, we perform instantaneous analysis of electrical properties at specific times and solve for time values that satisfy specific conditions. Finally, we examine instantaneous power, power delivery over time, and energy transfer during a back-to-back charge and discharge process. Long story short, any energy stored in the capacitor during the charge phase can be later retrieved for use during discharge. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.